Hi guys, welcome to this set of videos. What we're going to begin to do now here in geometry is we're going to start taking a look at the relationships that we can see inside of triangles, the angles inside and outside of triangles, as well as take a look at some special cases with triangles like an isosceles or an equilateral triangle, right? So really over the next couple of sections and the next few sets of videos, we're going to focus primarily on triangles and just sort of take a look at the different little relationships and things that we can learn about triangles. So let's just jump right into this. What we're going to start with here is taking a look at the interior and exterior angles of triangles. But as always, we start with an essential question. Here's what our essential question is for this set of videos. We want to know, what can we say about the interior and exterior angles of a triangle? And as a result of what we know about triangles, what can we say about other polygons? We'll talk about that in a second. Again, the way that we're going to do this is we have several objectives or learning targets. These are the things that you'll need to be able to do or what you'll need to know in order to answer that essential question. So as we go through our notes, these are essentially the things that we're going to hit, the highlights of the notes, right? So let's go ahead and jump right into this. First, triangles. Let's go ahead and explore some things about the interior angles of triangles. What I've done, I've simply drawn a triangle for you and I have little arrows pointing to the angles of that triangle. Now, what I'm going to do is I'm just going to rip those angles off, right? So if I drew this triangle on a sheet of paper, right, I just tear that angle off, tear that angle off, I tear that angle off. So I've got my little angles here. I've got this angle right here, I got this angle right there, that angle right there. That's all I've done, right? I've just ripped those three corners, those three angles off. And what I'm showing you here is I can put those three angles together and look what it does. That's a straight line. Remember, a line is an angle of 180 degrees. So here's what this tells me. The interior angles of a triangle, if I were to put them all together, if I were to add them, right? This angle plus this angle plus this angle, it's going to give me a line, 180 degrees. This is actually an idea we've looked at before, but now we're going to prove it to you. All right, so this is the interior angles of any triangle. Any triangle, here's what we know. I'm going to, in order to prove this, in order to show that this is the case, I'm going to use what's known as an auxiliary line. I'm just simply going to add a line to my diagram. So this is the triangle, right, that I've got for you guys. I'm just going to add this little auxiliary line right up here. Now, why do I add that line? Here's the reason why. I'm going to add this auxiliary line so that it is parallel. This guy is parallel to this guy. Why would I do that? Here's the reason I would do that. I now have a transversal. I have a transversal right there. Well, guys, we know all kinds of things about parallel lines cut by a transversal. In fact, what we know about parallel lines cut by a transversal is that alternating interior angles are congruent. So here's what I know. Angle 1 and angle 4 have to be congruent, which is exactly what I tell you right there. Why? They're alternate interior angles. Alternate interior angles of a transversal are congruent. But I have another transversal. Ignore for a second. Oh, I got a little crazy there. There we go. Ignore for a second. Just ignore that blue line. I have parallel lines. These green lines are parallel. One of them is an auxiliary line. It's a line that I added to the diagram, but that's okay. Parallel lines. That yellow line is now a transversal cutting through parallel lines. What do I know? Well, I know that the alternate interior angles are congruent. This guy and this guy, which is exactly what I tell you right here. Angle 3 and angle 5, they're alternate interior angles. They must be congruent. They have to be the same measure. Well, look at this. Angle 4, which is the same as angle 1, and angle 5, which is the same as angle 3. Don't forget that they're the same, right? 4, 2, and 5. What do those three angles have to sum to? Angle 4 plus angle 2 plus angle 5. Guys, what does that have to sum to? 4, 2, 5? Makes a straight line. They must sum to 180 degrees. They have to. Look, they make a straight line, right? Those three angles added together gives you a line. So 4, 2, and 5 must sum to 180 degrees. But hold up a second. Angle 4 is congruent to what? Angle 1. So, angle 1. Since 4 and 1 are the same, I'll just substitute a 1 for 4. They're the same angle. And angle 2, just keep angle 2. What is 5? Angle 5 is congruent to who? Yeah, 3. Now, here's the deal. If angle 4, which is the same as angle 1, angle 4 plus angle 2 plus angle 5, which is the same as angle 3, if these three angles sum to 180 degrees, what do these three angles have to sum to? Yeah, they have to sum to 180 degrees. They have to. But angle 1, 2, and 3 are what? 1, 2, 3. Angle 1, 2, and 3 are the interior angles of a triangle. What you guys just did is this right here. You have just proven that the three interior angles of any triangle, if it's a triangle, the three interior angles must sum to 180 degrees. They have to. You don't have a choice. If it's a triangle, the interior angles sum to 180 degrees. Now, let's extend this idea to any polygon. Stick with me. Here's what we've got. A polygon, right? To determine the sum of the interior angles for any polygon, right? We can use this idea of the Triangle Sum Theorem. Okay, so a polygon, poly simply means many, right? And essentially it's a shape of many sides, right? So a triangle, tri being the prefix for 3, so a shape with 3 angles, right? A polygon is going to be a shape of many angles, more than 3. In this case, I give you a quadrilateral, which has 1, 2, 3, 4 angles. But here's what we're going to do. I can divide this quadrilateral into 2 triangles, right? I split it right down the middle, right there. I have a triangle on top and a triangle on the bottom. Stick with me for a second. The interior angles of that top triangle must sum to what? Yeah, I know that this top triangle, the interior angles must sum to 180 degrees, right? This angle plus that angle is 180. But I know then that this bottom triangle, because it's a triangle, must also sum to 180 degrees. This angle plus this angle plus this angle. Since this polygon, this quadrilateral, contains 2 triangles, what is the sum of 1, 2, 3, the 4 angles inside my quadrilateral? Well, since this triangle sums to 180 and this triangle sums to 180, in order to find the sum of the angles in the quadrilateral, this one plus this one plus this one plus this one, right? All I have to do, 180 plus 180. Just add up the number of triangles inside the quadrilateral to find the sum of the angles for that quadrilateral. Here's the way it's going to work. There is a fancy equation for it. We'll go back and forth between the two in a couple of example problems just to make sure that you've got it. Here's the equation. The measure of the angles is going to be n minus 2 times 180 degrees. Now, n is the number of sides. Okay, here's the way that this is going to work. I count up the number of sides. 1, 2, 3. I have 4 sides. I plug those into my equation. 4 minus 2 times 180. Well, 4 minus 2 is 2, right? 2 times 180, 360 degrees, which is exactly what I got by looking at my 2 triangles. Top triangle, bottom triangle, both of which have to sum to 180. 180 plus 180, 180 plus 180 is 360. So either way, whether you split your polygon into triangles and find the sum that way, or use our fancy equation, count the number of sides minus 2 times 100, whatever, you get the exact same answer either way. And we're going to practice using both of these. 360, 360, you get the same answer either way. Stick with me. Let's try a couple more together. You'll see exactly what we're talking about here. All right, I've given you several polygons. I want to know what is the sum of the interior angles. In fact, that's right. Determine the interior angle sum, right, of each polygon. All that means is add up the sum of the interior angles. What would you get, right? If I added the sum of all of the angles, what does it add to? Okay, here we go. Triangle. That one we already know. We already know that a triangle must sum to 180 degrees. So 180 degrees. That one's easy. Okay. Quadrilateral, we just looked at it above. I have 2 triangles. So 180 plus 180, 360, right? We already did that one above too. Here we go. Here's my next one. Now again, the way to draw these triangles, right? If I just give you a quadrilateral, right? Pick a vertice. It doesn't matter which vertice. I could just as easily have chosen this vertice and drawn my triangles. I could have chosen this vertice and drawn my triangles. Doesn't matter. Please do not obsess over which. There's no right or wrong vertice. Pick a vertice. Draw your triangles. Just draw the triangles in there. Please notice whichever vertice you pick. I picked this one, this one, this one, this one, and this one. Whichever vertice you do pick, and it doesn't matter which one, whichever vertice you pick, you will not be drawing a line to the 2 vertices adjacent to it, right? The vertice just to the left, no line. The vertice just to the right, no line, right? You'll skip the vertices that are right next to the one that you picked and just draw your triangles to the rest of the vertices. So because I picked this one, skip that one, draw my line, right? Since I picked this one, I skip that one, do the next vertice, right? Same thing here. I picked this one, so I skip the 2 right next to it, I draw my lines to the rest of them. I pick this one, skip the 2 vertices right next to it, draw my lines to the next one. And we'll get lots of practice with this when we take a look at a couple of example problems. But let's keep going with this idea. Make sure you got a calculator with you in order to do it. I've got 1, 2, 3 triangles. What does that mean? Well, that tells me the sum of the interior angles should be 180 plus 180 plus 180. 180 times 3, I get 540 degrees. Now, we got that fancy equation. Do you remember what the equation was? N minus 2 times 180. N is the number of sides. I'll count them up. 1, 2, 3, 4, 5. So plug it in. 5 minus 2 times 180. 5 minus 2 is 3. Oh, sorry, hang on. Please notice, number of sides minus 2 is 3. How many triangles was there? Right? What you're doing is figuring out how many triangles fit inside the polygon and then multiplying by the sum of the interior angles of a triangle. Right? Exact same thing here. I have 1, 2, 3, 4 sides. 4 minus 2 is 2. How many triangles was I able to draw inside the quadrilateral? 2. Look. 1, 2, 3, 4, 5, 6. 6 minus 2 is 4. How many triangles do I have? 1, 2, 3. Not that hard. Not that big a deal. Same thing here. 1, 2, 3, 4, 5, 6. 7 sides. 7 minus 2 is 5. 1, 2, 3, 4, 5 triangles, right? Love it when it makes sense, right? So either way, whether you draw the triangles or use the equation, you're going to get the same answer either way. And we'll go back and forth between the two. Anyway, what we were doing was we were calculating the interior angle sum. Let's keep going. I have 4 triangles. So 4 times 180, I get 720 degrees. So all of the interior angles must sum to 720 degrees. Keep going. 5 triangles times 180, 900 degrees. What do I got? 6 triangles times 180 looks like 1080 degrees. Again, whether you use triangles or count the number of sides, subtract 2, multiply by 180, you'll get the same answer. Get the same answer either way. All right, a couple last minute things here about polygons before we take a look at a couple of example problems and really kind of drive these ideas home. First of all, a convex polygon. Remember, there's 2 phrases you would have learned probably back in middle school science: convex and concave. Convex and concave. So this idea of convex, simply when it comes to a polygon, means this: all of the interior angles are less than 180 degrees. Just a fancy way of saying this, right? All of the interior angles measure less than 180 degrees. Here's what that means. All the vertices of the polygon point outward, away from the interior, right? Take a look at this. Every single one of these angles, right? That vertice is pointing away from the inside, pointing away, pointing away. All those vertices, right? They make an angle that's pointing away from the interior of the polygon. That's all we're saying right here. A convex polygon simply means all of the vertices less than 180 degrees, they're all pointing away from the interior of the polygon. That's all it's saying. And then one more quick one, because we'll see this show up in problems later on. A regular polygon. In a regular polygon, all of the sides have the exact same measure. Every side is the same length. They all have the same measure. We'll come back to that a little bit later on. I'll remind you of it when we see some problems. And finally, we talked about it above. Here it is right there. Your equation. How do you find the measure of the interior angles of a polygon? The number of sides minus 2 times 180. Or draw the triangles. Count the number of triangles, multiply by 180. All right. I know I just threw a ton at you guys. I promise on the next page of the notes, we'll look at several example problems together to really sort of drive this stuff home and make sure you understand it. So head on over to the next page of the notes. I'll meet you guys there.